Hi everyone, this is Mrs. G, and today we are going to be talking about inverses of functions. So I have a quick warm-up for you guys right here, so please use transformations to complete the following task. You can pause the video and give this a try, and we'll check your answer in just a few seconds. Okay, go ahead and check your work here. So this is a quadratic function. So we know that a quadratic function, the parent function, has a vertex at the origin, and it looks something like this. So in terms of transformations to what you would see here in this quadratic, you can see that we have a vertical reflection over the x-axis, and we have a shift to the right 30 and down 8. So those we can put into our function. We have the negative out front, which is the reflection, and then we have x minus 30, so that shifts it right 30, and then we have the minus 8 on the outside. But for this, you can also see that there's going to be some type of stretch or shrink, so we have this a value out front that we still don't know. We can solve for a by substituting any other known coordinate into our equation for x and y, and then we can use that a value in our final answer. So I substituted the coordinate for negative 25, so you can see my x value is replaced with 4, and my y value was replaced with negative 25, and then I solved for a, so my a value is 17 over 676. So the final answer looks like this. So the negative is a reflection, this would be a vertical shrink by this factor, and then right 30 and down 8. Okay, going back to our topic today, which is inverses of functions, I want you to consider a scenario. Let's say this linear function, c equals 3.5 times g, models the cost, c in dollars, for buying g gallons of gas at the Costco gas station. So we have this linear function, and again, c equals 3.5 g. So what is the input? So our input here is G, which is the gallons of gas. And then our output would be the cost in dollars, right? So this model, we could say, hey, I purchased 5 gallons of gas. And then our output would be what the cost is. Hey, I purchased 7 gallons of gas. What's the cost? I purchased 20 gallons of gas. What's the cost? So imagine a scenario now where instead you actually want to model how many gallons you could buy depending on how much money you had to spend. So in this case, what if your input was the cost, right? You say, hey, I have $15. How much gas can I buy? So meaning your output would be the gallons of gas. So again, depending on what you're trying to do, this might be a more useful model. What can we do if we want this to happen? So this would actually be considered an inverse of our original model, because you'll see that instead of the input being gallons and the output being cost, our input is the cost and the output is gallons. So anytime you want to swap the input and the output of a function, you're essentially going to be finding the inverse of that function. So this is kind of a practical example of why would we want to be able to do this process of finding the inverse. Here's why. So it's to help us find a model that's maybe more useful for our scenario. So what is the inverse of a function? The inverse of a function reverses, again, or it swaps the input, which is the x value, and the output, which is the y value of your function. So just like in that last example. The inverse is going to be denoted with this symbol. It looks like it says f to the power of negative 1 times x. That's not how we read it. It's not what it means. This, again, is the symbol for inverse, and we would read it as f inverse of x, or the inverse of f of x. So again, this is a notation for inverse. It does not mean f to the power of negative 1, okay? So a few different representations of what a function is. Like I said, it literally swaps the x and y values of everything. So if you have coordinates from your original function, x, f of x, if you want the coordinates of your inverse function, you literally swap the x and y values. So you would have 4, negative 2, 3, negative 1, 5, 2, and negative 1, 3. In addition to swapping the x and y values of the coordinates, the domain and range also swap. So if your original function has a domain of negative 2 to infinity and a range of all real numbers, our inverse would have a domain of all real numbers, and our range would be negative 2 to infinity. And last, a graphical representation of what an inverse looks like. Because of the fact that we're actually swapping the x and y values, this actually will cause our graph to reflect over the line y equals x. So here's the line y equals x, just that linear equation through the origin. So it's actually going to reflect over that line. So anything on that line will stay the same. But for instance, this coordinate right here, it's going to go to the other side of our line. So it looks like this. Again, we're swapping the x and y values. So instead of doing 3, 4, we have 4, 3. And then here for this coordinate right here, instead of being 1, 0, we have 0, 1. So you'll see it's the same distance away, but on the other side of your line y equals x. Here it's like a diagonal across. Here it's a diagonal across. Here we're a diagonal and a half. We can do that in the other direction. So again, we're reflecting over that line y equals x. And that's what happens when we swap our x and y values. So just graphically, what happens when you find an inverse, what does it look like? Just a reflection over this line. Okay, how can we find an inverse algebraically? So it's pretty easy to do. What you do first is you swap the x and y, the location of x and y in your equation, and then you just solve for y. You isolate y. And then once you've done it, now you're going to make sure you write it with the proper notation using that f inverse of x symbol to show that it is the inverse. Now, once you've done this, we can actually check to make sure that our work is correct using what's called a composition of functions. That's where we're actually plugging a function into a function. So there's two different ways you can check. You can do f of f inverse of x, meaning you substitute the inverse into the original function and you simplify. If you did it correctly, you should end up with just x. That's one of the definitions of a function. Or you can do the opposite. You can do f inverse of f of x, meaning you're substituting the original function into its inverse, and you simplify to see what happens, and you should just get x. So that's how you can verify algebraically that the two things you came up with actually are inverses. Okay, let's give this a try together. So we're going to find the inverse, and then we're going to verify it algebraically. So here, again, the first step is to swap x and y. I want to remind you that f of x is interchangeable with y. So we're going to swap where those are. So we're actually going to write it as x equals y minus 2 over 8. And now we're going to solve for y. So the first thing I need to do is multiply by 8. So 8x equals y minus 2, and then add 2. So y equals 8x plus 2. Since this is our inverse, now we're just going to make sure to write it with the proper notation. And this should be it. Now let's check to make sure that this is correct. Let's do f of f inverse of x. So what does that mean? We take our original function and we're going to substitute our inverse into it. So I'll write it like this. F inverse of x, right, is 8x plus 2. So we're taking 8x plus 2 and we're going to replace it wherever we once saw an x. So here, 8x plus 2 minus 2 over 8. And let's simplify that. So here we have 8x plus 2 minus 2, so 8x over 8, which is just x. So when we did f of f inverse of x, you can see that it simplified to x, which verifies that we did our work correctly. You do not need to do both versions, but I just want to show you that it also works if we do f inverse of f of x. So again, we're taking our original function and substituting it into our inverse. So f inverse of f of x is equal to x minus 2 over 8. So let's substitute that into our inverse. So where I see an x, I'm going to replace it with this. So 8 times x minus 2 divided by 8 plus 2. This simplifies to 1. So what I have left is x minus 2 plus 2, which again is just x. So again, you do one or the other. You don't need to do both. You can, I guess, if you have extra time and you want to be extra sure. But this is how you can verify algebraically that your answer is correct using that composition of functions. All right, at this moment, please go ahead and pause the video and give this one a try, and we'll check your answers in just a few seconds. All right, go ahead and check your work here. Please be careful with this negative out front. It doesn't just belong to the 2x. If you want to distribute it to the full numerator, that's fine. But if not, you could always divide it out in the first step, which is what I did. So for your inverse, you can write it in two different ways. You could say negative 5x minus 3 all over 2. If you write it like this, notice that this is all part of your numerator. Or if you'd like, you can factor out the negative and put it out front, and then this would become positive 5x plus 3. Either way is fine. And then here you can see I verified my work using that composition of functions, and it was equal to x, so I know that I did it right. So now I want to talk about a really common question I get. Is the inverse of a function always a function? So to answer that, let's look at two different types of functions. These are both functions. Let's actually look at m of x first. This input has one output has one output, so on and so forth. And you'll notice that all of the y values are also unique to the x values. So remember, this is what we call a one-to-one function. And let's see what the inverse looks like and see if it would be a function. So let's do m inverse of x. Remember, to find an inverse, we would just simply swap the x and y values. So we have negative 6, negative 4, 2, 4, 6, negative 3, negative 8, 0, 2, 6, and we would also swap the arrows. So negative 3 goes with 6, and that means negative 6 goes with 3. Here, negative 4 goes with 6, so this went with this. 2 goes with 0, 4 goes with 2, and that 6 goes with the negative 8. So it looks like this. So you can see that we have a function, right? Every x has only one y, and we actually have another one-to-one function. So the inverse in this case is a function, and it is also a one-to-one function. So that works, but is that always the case? So let's look at a different type of function. So again, this is a function. Every input has only one output, but some of the outputs are shared. Well, specifically 9 is shared by two different inputs. So it is still a function, but remember, we call this a many-to-one function. So let's actually see what happens when we look at the inverse representation. So swap the x's and the y's. Negative 6, negative 3, 0, 3, 6. So here, 36 goes with nothing. Okay, 9 actually goes with negative 6 and negative 3. So right off the bat, maybe I'll do this with red arrows. Right off the bat, you can see that our inverse is not a function. It doesn't matter what's going on here because we can already see this input has two different outputs. So in this case, our inverse is not a function. So we can generalize that if you have a one-to-one function, the inverse will also be a function. But if you have a many-to-one function, your inverse will not be a function. So let's talk about how we can test to see if an inverse will be a function if we have the graph. So this is called the horizontal line test. So remember, we use a vertical line test to see if something is a function. We use a horizontal line test to see if it's a one-to-one function, which means that its inverse will also be a function. So same idea, except with a horizontal line. If your graph crosses more than once, then we know that this is a many-to-one function. And that means that the inverse inverse is not a function. So if it fails that horizontal line test, the inverse is not a function. Here we just have a linear equation like this. This passes the vertical line test. So this inverse is a function. So the horizontal line test, again, can be used to determine whether or not your inverse is a function. The vertical line test is to determine whether the function, the original graph, is a function. Okay, so for example 2, we're going to look at the graph, determine if its inverse would be a function, and then if it's not, we're going to see if we can actually find a way to restrict the domain of our original function to make the inverse a function. So again, this quadratic definitely fails the horizontal line test, so we would say the inverse is not a function. So our goal is going to be to turn this many-to-one function maybe into one-to-one function. And we can do that by restricting the domain. So we want to, for a quadratic, we can do this pretty easily. We can start at the vertex, and then we can either restrict the domain to just the stuff to the right or just the stuff to the left, right? If I take out the u part and I just make it a line, then it will no longer fail the horizontal line test, and our inverse will be a function. So we have two possible answers here. We can restrict the domain to everything greater than or equal to 2. So our domain would be 2 to positive infinity. Or we could restrict the domain to everything less than or equal to 2. Or it could be negative infinity to negative 2, including them. So if we did that, again, imagine maybe that first scenario, our graph would look just like this in blue. And then imagine that left part of our graph, we're no longer using it. This would pass the horizontal line test, so we could find an inverse that is a function. Or likewise, again, we could just use this half of our graph. So either of these restrictions would work for this problem. All right, here's the last example. Please pause the video and give it a try. Okay, so again, this function fails our horizontal line test, so the inverse would not be a function unless we restrict the domain. So we could either say restrict the domain to everything greater than or equal to negative 3, so negative 3 to infinity, which would just be the right half of our graph. Or we could say negative infinity to negative 3, which would just be the left half of our graph. But either way, find the vertex and then just define everything to the right or the left of it. Okay, that's all for today's video. Thank you so much for watching.